Okay, let's get started. Welcome everyone. Good morning, good afternoon, good evening, wherever you are. This is the Phoenix Area Group tinyML talks. Today we have a very exciting seminar on system support for efficient multi-resolution visual computing on low-power embedded systems by Dr. Robert LiKamWa. Before we start, I'd like to acknowledge the tinyML talk sponsors that make these talks possible: DeepLight, Kitso, Edge Impulse, Reality AI, Maxim Integrated, and SynSense. Additional sponsorships are available. Contact Betty at tinyml.org for more info. And just a reminder, our next tinyML talks are next Tuesday, September 15th. We have Hiroshi Doryu talking about tinyML as a service, bringing ML inference to the deepest IoT edge. Vikrant Tomar and Sam Meyer from Fluent.ai. We're talking about speech recognition on low-power devices. These webcasts will start at 8 a.m. Pacific time. Each presentation is about 30 minutes in length. If you're interested in presenting or giving a talk for this seminar series, please contact talks@tinyml.org for more information. So today it's my pleasure to introduce Dr. Robert LiKamWa. Dr. Robert LiKamWa is an assistant professor at Arizona State University. He leads the Meteor Studio, which explores research and design at the software-hardware interface for mobile augmented reality, virtual and mixed reality, and visual computing systems. Prior to coming to ASU, Dr. LiKamWa completed his bachelor's, master's, and doctor's degrees from Rice University. He's received many awards, including the NSF Career Award, the Google Faculty Research Award, and a Best Paper Award at Mobius 2013. And just for some logistical reasons for this talk, you can use the Q&A functionality to ask questions. I will be periodically asking Robert questions during the presentation and afterwards. In addition, the slides and the recording will be made available afterwards, both on YouTube and in the tinyML forums, so that you can follow up the conversation. And with that, I'll have Dr. Robert LiKamWa take it away.
Hey everyone, thanks for coming, and thank you, Suren, for inviting me to this tinyML and for moderating this whole thing. So today, like Suren said, I'm going to be talking about system support for efficient multi-resolution visual computing on mobile systems. This is in the context of tinyML because we want to have ultra-low power devices at the edge. We want to have low power machine learning. And the big problem is that vision is power hungry. That's a very obvious statement. I think it's something we can, if we have experience, we can agree with that statement. And another statement we can agree with is vision is power hungry, especially at high resolutions. So when you're dealing with just a lot of pixels coming into your sensor, being sensed, converted from the analog to the digital domain, being stored in DRAM, being read out of DRAM, all those processes having to be done on so many pixels is highly problematic for trying to be energy efficient, trying to be low power. But the upside is that vision doesn't always need high resolution images. If you're dealing with an object recognition task and your objects are very well posed, they occupy a high percentage of your frame, then you can deal with a lower resolution image and still be able to see what's inside of the image. And not just as a human, but our visual networks as well will also be able to recognize that there are keys inside of that image, for example. Or if you're doing augmented reality, whether you're doing detection of surfaces so that you can know where to place objects, or for example, looking at a marker and seeing that the marker is far away, you might need high resolution, but when the marker comes closer to your camera, then you can actually use a lower resolution and still get away with having a low error in your tracking. And then you're going to be able to use that to overlay these different virtual objects on top of your physical scene quite precisely, despite operating at a low resolution. So it's nice if we could take advantage of those opportunities and have these trade-offs between high and low resolution. And indeed, people have been doing this for decades of being able to say, well, I can turn my compute to operate on fewer pixels. And so then I can just skip looking around at the whole, from looking around at the whole image to only looking around at a smaller resolution of the same thing. So then I can save on computational cost. But it's obvious that we need to have that operate at a sensing pipeline as well so that we can fully exploit different energy savings opportunities. And so in today's talk, I'll be talking about two different works that we've been doing to leverage this concept of dealing with multi-resolution visual computing. The key is that we also need to have system support for it, which is what these two works are about. The first work is something that I did in my graduate school days. The second work I'll talk about is something that's done in, well, my graduate students' graduate school days, which is these days. We'll go through both of these projects in the context of this talk. So, like I said, right, we've got this nice possible trade-off here where if image sensing is energy proportional, then that means that if you're dealing with a high resolution, then maybe you take up some energy per frame. But if you're dealing with a much lower resolution, then you should take less energy per frame. And if you look at sensors that capture high resolution images, you'll see that they're usually higher power than sensors that capture low resolution images. But what turns out is if you use the same sensor to capture high resolution images and low resolution images, then you'll notice that when it's in low resolution mode, it actually consumes a high power consumption and a high energy per frame. So this was actually surprising to us when we saw this, when we hooked it up to some power measurement devices to see that why is this the case? That if we're dealing with the same sensor that's capturing 1 megapixel at, we were doing 3 frames per second for this particular sensor, same sensor, same frame rate, and we're doing 0.1 megapixels, you'd expect it to be 1/10 of the power consumption, but it's not, it's much higher than that. And so we wanted to investigate why that might be. And this was back in my grad school days. I was working with Microsoft Research on this project as well, with Victor Bal and Bodhi Priyanta and Matai Philippos and my advisor Lin Zhang at Rice. And we were all mystified in looking at this. And we noticed that, well, we can hook up all these messy wires. Again, this was in my grad school days. Probably would do it a little bit differently now. But the point is that we actually were able to monitor the power consumption and look at these waveforms. And these waveforms are kind of interesting because you see that there's actually this raised component. And what we realized is that is actually due to the pixel readout process, where it's doing those conversions, where it's reading those pixels out over the interfaces. And then there's actually this idle period, which is really just spacing your frames out until you're ready to sense the next frame. And so it's this duty cycle between active periods and idle periods that is actually constituting the energy per frame. If you look at the power is on the y-axis there, the time is on the x-axis there, so power times time is your energy. So the area under that duty cycle is your energy per frame. And if we stare at this a little bit, then we'll start to see the picture of why we have such limited energy proportionality. Because when you're at high resolution, you'll be occupying most of your time in that active region and less of your time in that idle region. And if you're in low resolution mode, then you'll be occupying less of your time in the active region and more of your time in the idle region. But that means you're still consuming power when you're in that idle period of that duty cycle. And so that idle power is exactly what it is that's limiting energy proportionality. We tried this across 5 different sensors. They have different active to idle ratios. Some of them, the idle power is 90% of what the active power is. Some of them, the idle power is like 50% of what the active power is. But regardless, you're burning all of that power just waiting for your next frame, for the timing. And so what we wanted to investigate was whether there was some driver level manipulation that we could do in order to be able to create the savings that we really want to. And instead of operating at that red line at the top, operating more at that green diagonal line so we can save energy when we're dealing with lower resolution images. And so we came up with 2 techniques, and they were inspired by computing techniques, but 2 very simple techniques at the driver level where we were able to create optimizations to enable this energy proportionality. The first was aggressive power management. If you're not using the sensor, you might as well turn it off, right? Turn off the lights when you leave. So we can actually do that. And sensors actually give you the opportunity to do that. The sensor hardware gives you a standby mode, which is often used for preparing your camera to take a snapshot. So if your driver actually exploits that standby mode on this duty cycle, you can actually put your camera in an ultra low power standby mode until you're ready to capture the next frame. And so if your driver manages that control, which is well capable of doing, you're able to save all of that idle power. You're able to discard all of that idle power, so you can save a lot of energy per frame. Now there's a caveat here. You do need to turn on your sensor early enough, have it out of standby mode in order for it to receive the light and expose the pixels to sensed values to sense the light. So it does need to be on for some exposure time before the active power, but it does allow you to throw away the rest of that idle time and idle power that comes with it. And so this aggressive power management is of course very useful. What it ends up being extremely useful with, though, is also being paired with pixel clock frequency optimization. Because when you're only dealing with that orange active power region, then you can do something that's been well explored in the computing domain, which is do some frequency optimization, right? We've heard of DVFS, dynamic voltage frequency scaling. Similar techniques can apply as well to image sensors as well. When you operate with a slower clock, it takes longer for you to read out more pixels, but it does reduce the active power. On the other hand, with a faster clock, it takes less time to read out pixels because you're able to read them out faster, but it takes more power to run. And so you can do your calculus 1 exercise of saying, well, how do we minimize the area under this curve? And it turns out to be a function of your pixel count and your exposure time to choose what is the optimal frequency you should use in order to minimize that area under the curve, given your task at hand. So again, your pixel count and your exposure time. So this together allows us to, these two techniques allow us to actually save a lot of energy per frame and lead to much lower power of image sensing. So if we look at this curve here, what we're seeing is frame rate on this depth axis and pixel count on this x-axis. And the power is on the y-axis. So what you're seeing is that at high pixel counts and high frame rates, we're consuming roughly 400 milliwatts of power. And at a much lower pixel count and frame rate, you're going to see it goes down to about like 280, for example, milliwatts. So this is before we apply our techniques. This is what this kind of curve looks like. Wherever you go in the pixel count by frame rate space, you're still operating at least that 280 milliwatts or higher. But after we apply our techniques, you'll see it takes a different curve. We didn't remove that other curve at top, but the curve that we're talking about now is the one underneath that, where you're seeing the greens and the teals and the blues as we're able to throw away that idle energy. We can now save all that energy and operate at much lower power consumptions when you're dealing with low frame rates and pixel counts. So this allows us to go from, for example, 280 milliwatts to 20 milliwatts for operating at the same resolution, same low resolution of 0.1 megapixels and same low frame rate of 3 frames per second for the same sensor that's able to capture 5 megapixel images. And so this is the work that we're talking about here. We need driver level support for this type of activity to be able to actually have multi-resolution visual computing and, more importantly, exploit the energy saving opportunities of multi-resolution computing. Suren, do we have any questions in the feed?
Yes, Yu Lu was curious if there was any, is the power proportional to the sensor's physical pixel size, or if you investigated that?
We didn't notice, so actually we weren't able to really investigate that because we were not able to have the ISO the same sensor architecture, for example, with different pixel sizes. I don't expect it would change, but but I'm not an expert in that space. It doesn't seem like it would be the case. Now, it's difficult for us to make that judgment because while we were looking at different sensors with different sensor pixel sizes, there are many other aspects that can change the power characteristics of the sensor.
And maybe I could follow up with the second question, which is it always, in your studies, was it always good to remove this idle time, or was there any cases where, or any operating scenarios you could think of where it is worth it to keep that idle energy?
Yes, so if you're operating at a very high frame rate, then it's actually, well, with a high frame rate and a high resolution, you don't actually have the opportunity to throw away that idle power anymore because your exposure time may be long enough that you need to have the sensor on while you are reading out other frames. It's the beauty of the rolling shutter architectures is that you're able to read out while you are exposing your frames, or the global shutter architectures as well. But the timing of being able to expose while reading out is important in those cases. But where you're operating at low frame rates and low resolutions is where you can really take advantage of these techniques and operate in these modes. Great question, thank you.
Great, thank you. And I'll just remind the audience that you can ask questions and answers with the Q&A tab as Robert continues to talk.
Okay, thank you, Suren. So that's the first work saying that, look, vision is power hungry, especially at high resolutions. Now we can actually exploit this at the image sensor level and be able to throw away wasteful energy when we're dealing at low resolutions, right? But what we're seeing in the computing world as well is that, well, vision is power hungry, especially at high resolutions. Well, let's see if the same thing that we saw with the sensors is true with the computing. It turns out that you can actually get 70% of savings on the compute when you're actually operating at lower resolutions. If you're seeing here from 960p computing for doing augmented reality marker detection versus 480p, we're saving that 70% here on this Jets Integra X2 board of processing different image frames as they come in. And what we found out through benchmarking is this is largely due to DRAM, is due to memory accesses, because you're dealing with sending lots of pixels to your memory, reading lots of pixels out of your memory, so that high bandwidth, that high throughput rather, is what's causing this high power consumption. So we want to be able to then, on the computing side, also be able to say, hey, we want to deal with low resolution data when we opportunistically don't need it. So the example that I had earlier was marker detection. When you're very close to the marker, you don't need as much resolution. You can operate with fewer pixels and still get your same good results. When you're far away from the image, then you're going to want to actually operate at high resolution so that you get the precision that you need for placing your objects correctly. Great, sounds great, right? So we're like, okay, well, let's just do it, right? I mean, people have been talking about this for decades, let's just do it. Turns out it's not that easy. When you actually try to reconfigure your resolution on the fly, you incur what we were seeing and what we're calling a latency penalty here. I hope you can see this through Zoom. It's cutting to black. What we did is we designed this app. It's running on Linux v4L2, the video for Linux 2, on this Jetson TX2 board. And every time you're trying to change from high resolution to low resolution, so as the marker gets closer, you can go to low resolution, you're seeing it cut to black. That cutting to black is a visible gap, and that's due to the reconfiguration. We'll explore why that happens in just a bit. But we're like, okay, maybe this is just a fluke, right? This is just the Linux v4L2 architecture. Surely in like mobile commercial systems like Android and iOS devices, oh, no. Actually, we see the same problem here. Every time you change the resolution from high to low, low to high, you experience this blackout period. So this prohibits application developers from doing anything. iOS, we see the same thing. It prohibits application developers from doing anything that exploits this concept of multi-resolution visual computing, because if they wanted to be able to say, okay, so occasionally I want to go to low resolution, occasionally I want to go to high resolution, they can't actually exploit that opportunity because it would create this detrimental effect to their users, that they're seeing the screen turn off and on. Like it would create jarring effects for the users who are using these applications. So we wanted to investigate what's going on here, and why is there this cutting to black reconfiguration latency period here? Is it in the hardware? Is it in the operating system? Well, we actually already knew from our previous characterization, from that previous paper, hardware is not the culprit. In hardware, you can change the resolution on the fly, actually, and it can do so without dropping a single frame. The data sheets show that you can actually change the hardware registers, and the effective, by the next frame, the sensor will actually change its resolution. It'll change its characteristics. It'll start reading out data the way that you want it to. So hardware is not the culprit. And we saw that before. We tried it again with our newer sensors, same thing. It's actually not the problem here. Which means that the problem is in the software, right? And it means the problem is in the operating system. And the reason for this is that in the operating system, the reconfiguration procedure, that is reconfiguring from low to high or high to low, your system will go through a sequential procedure inside the media framework. And that's going to require the application to invoke several really expensive system calls, some of which relate to allocating memory, freeing and allocating memory. So that's going to be the culprit here, because when your application wants to change its resolution, the first thing it's going to do is the application sends a resolution request. That's the level of abstraction. The application doesn't know anything else after that, of course. So it sends this request. So now it's up to the media framework to do its job. Well, the first thing that happens is that the media framework actually turns off the current streams so that it can actually change the streams. So it turns off the current streams, and that's where it's turning to black. And then it unmaps the buffer with which it's holding the frames, freeing them up. And then it goes ahead and sets the sensor format. So it changes that hardware register value in order to change the sensor, the format that the sensor is reading out at, which we covered on the last slide. After that, it will memory map a new set of buffers. So it's going to now allocate different memory for this set of frames. And then it's going to start up the new streams, and then your application gets the images and everything can run again smoothly. But this is the problem here, is that every time that you want to reconfigure, going from low to high or high to low, you're going to have to go through that big black loop that you're seeing up there, circled in red, and go through each of those different steps. Unmapping the buffers, memory mapping new buffers, and then you can start up your new stream. That's what's happening during that black period. So what can we do here? Well, we aspire to have a reconfigurable media framework, which allows us to preserve the pipeline of existing frames. We don't want to throw away any frames that we already have captured. We also want to be able to change the resolution immediately and have that effective in the next capture. And then we want to be able to minimize the memory allocation, the format synchronizations of that memory across the video system stack. We don't want to lose things that are in the frame, that we don't want to have to reallocate our frame buffers, because that's very expensive to do. So try to minimize that unmapping and remapping of these frame buffers. So to do that, we introduce a different framework, which we call Banner. It's the Banner Media Framework. This name Banner, we came up with my grad student Jinhan and Saranya. We were working on this, and we were thinking about what a nice seamless kind of stream of frames might look like, and we said, okay, a seamless string is Banner. And then we also said, well, also this can also be a play on changing from big to small, like Bruce Banner from the Avengers. So we had this like pun going about Banner. And so in our paper, we said it's because of this seamlessness, but secretly we're like, it's actually because of the Hulk and Banner transformations. But in any case, this is our Banner Media Framework, which will allow you to change from high resolution to low resolution to high resolution without dropping any frames in between, completely seamlessly. And we do this by allowing our applications to reconfigure sensor resolutions with a media framework that only uses one ioctl call. The way we do that is by avoiding the repeated reconfiguration procedure, where we have the legacy v4L2 on the left. We can see that we can actually avoid that very large loop of going through the releasing and requesting of new buffers, and instead have a much tighter loop at the bottom here. This is achieved by two simple techniques. One is format-oblivious memory management, and the other is parallel reconfiguration. So in parallel reconfiguration, we do what we just said, is we reconfigure in parallel with the existing capture and processing of the frames. So instead of pausing and stopping your sensor stream and then doing reconfiguration and then starting up your sensor stream again, which would be sequential reconfiguration, we said, well, why don't we just execute the sensor reconfiguration inside of the same time that you're trying to process your frame? We can't do it inside of the capture period, but we can do it while the frame is processing. The capture period ends up being fairly short anyway, so you have a lengthy timing budget with which you can actually execute that sensor reconfiguration. So that's the first step, is we want to enact thread level concurrency and time that request to happen within the reconfiguration timing budget. So make sure it happens right when you're processing the frame. And so we can do that inside the media framework level in the operating system. The next thing we want to do is have a format-oblivious memory management. So have a one-time buffer allocation and have format-oblivious frame delivery. There's no need, we're saying, to unmap and remap new buffers. Instead, just reuse the same buffer space. Now, the key important thing is that we do need to keep track of where we are inside of that frame buffer, and basically give it the starting point as though you're dealing with large frames all the time, but you don't have to use all that space. You can leave a lot of it empty, and you'd be able to save on your memory transactions because you're operating with many fewer pixels as you're going through. So it's not like you're wasting memory throughput. You're wasting some memory allocation space, but you're not wasting the throughput, which is what really matters for power consumption. And then you're able to use that same space for 1080p frames, 480p frames, whatever p frames you want, as long as it's large enough to contain those frames. And then the media framework has a responsibility of communicating to the application of where those memory segments are for each frame, but it can do the arithmetic just fine. So we developed this memory management that is format-oblivious for this buffer allocation, and so for this format-oblivious frame delivery, and that allows us to then not have to do the mapping and unmapping of buffers every time that you need to do a resolution reconfiguration. And so through both of these, we're able to avoid the repeated reconfiguration procedure. We're able to actually save on all that time. And so what that results in is that now, instead of having those cut to black periods, we're actually able to change from high to low resolution, low to high resolution, with 0 frame drop, which you're seeing on the right side of this figure there. Does anybody have any questions at this point?
So I ask a question of Chandru Sakala, who asked, recently there's a lot of multiple cameras being used by different manufacturers, Samsung, Apple, so on. Does this framework, is there any issues with switching between multiple cameras, or how specific is this for camera architecture?
So it's a great question, but because you're absolutely right, is that most cameras, most devices these days have multiple cameras on them. And so with switching between those, if you've got a very nice image signal processor, you're able to actually have multiple streams going at once and be able to switch those streams without penalty. And so that's actually a totally reasonable way to do things. However, if you're going to be merging those streams through the media framework, you're going to have to combat these issues along the way as well. And you'll have to have these strategies to create this seamless reconfiguration between those sensor streams. So it kind of depends is what the point is here. Oftentimes, the reason why you have these different sensors is for different focal abilities. And so if they operate at the same resolutions, but different focal abilities, you won't have the issues of resolution reconfiguration. And so these issues that we're trying to solve here through the banner media framework are specific to where you're jumping from low to high or high to low resolutions.
And a second question from Sean Doyle was, can you get a similar scaling effect? I'm guessing a scaling effect in power is what they're asking here, by using compressed sensing or sampling at different resolutions.
So I think that those are excellent techniques that have been well studied about trying to computationally try to reduce your sensing workload, to reduce the number of pixels that are coming in. And I will point out that those are great techniques. The point that I want to make through these slides is that we need to have system support for those and other techniques. To have sensors and algorithms that are able to throw away data is important, but then being able to support it through driver level management to actually get the gains that we want, and to actually make the reconfiguration smooth and seamless and viable is actually a very important task as well. Not just an engineering effort, I would say also as well.
Okay, thank you. And to remind the audience, you can there's still time to ask more questions, and we'll have some time at the end of the talk.
Thank you, Suren. So to wrap up, these are the two techniques that we talked about here. One is this driver-based management for energy proportional image capture by being able to turn off the sensor opportunistically by putting in an aggressive standby mode, and then using that time then to play with the clock frequency, because now you have time to make the shape of your power times time curve either shorter and fatter or taller and skinnier, and you can play with that to make your area under the curve really optimal. So those techniques allow us to save orders of magnitude when you're moving around the frame rate and pixel count area. And then we also talked about the banner media framework, which allows us to use those kinds of changes in resolution from high to low, low to high resolution, without dropping a single frame in between and reducing the user's experience. So we're able to provide these through driver level or media framework level management and optimization here. And I think this creates a platform of support for reconfigurable resolution frameworks. And so we have ongoing efforts that leverage this and build upon it in multiple fronts, including looking at it in contextual use cases. Inside of augmented reality and mixed reality, people are talking about foveated rendering, where you want to render visual information to the user that is following their eyes and rendering at high resolutions in those periods and low resolutions elsewhere in the frame, so that you can save on your graphics workload. Well, we can use those same kind of strategies to save in the visual pipeline as well, the visual workload as well, and have some foveated sensing to actually also follow along with that, and build in the system support for that along the way as well. And then talking about adaptive neural networks that can work on variable size image streams. Right now, most neural networks work on fixed sized image streams. I think a lot of us are familiar with the 227 by 227 by 3 that many networks expect these days. And you have to crop your images to fit exactly that and resize and rescale them. But it would be interesting to consider neural networks that are able to work at high resolutions and low resolutions and be paired with this kind of reconfigurable resolution support, so that you can deal with that multi-resolution visual computing and get the precision that you want when it's needed, and get the energy savings that you want when you don't need that precision. With Suren, actually, I'm collaborating with him on software-defined imaging systems. He has a great talk, a tinyML talk from 2 weeks ago. So if you pull that up, you can learn more about that. But Suren's doing some really interesting work on thinking about variable bit depth sensors, looking at region of interest tracking, and bringing that from the past into the future of thinking about what that really means for developing these kinds of mechanisms of software-defined imaging. Trying to build in these sensor control loops that are finer grained, that are more flexible, that are more viable for the future of our imaging systems by introducing software-defined layers throughout the architecture. I also think we should be looking into cloud integration. I don't think we've discussed that yet, Suren, but maybe we will in the future. But I'm thinking about how the software-defined imaging also pairs with the emergence of these 5G networks, where we're able to have low latency, high bandwidth links to cloud support, what that means for our software-defined imaging system. So the software might move up and down the stack as far down as a sensor or the ISP or the vision processing unit or the CPU, and could go upwards towards the cloud as well. And a pet project, not pet project, but actually a main project of mine is fine-grained reconfigurability as well. So exploring the concept of multi-resolution, not just across frames, from frame to frame to frame, high resolution, low resolution, low resolution, but actually within the frame. Because not all areas of your frame need the same amount of resolution. And like I said, people have been exploring this in the concept of rendering, but I think there's a lot of fruit to be looked at when doing this on inside of the image frames for the image sensing, for the visual sensing tasks at hand. And so we want to explore that with variable spatial resolution as well as variable temporal resolution of what does it mean if we depart from the concept of having uniform frames with uniform spatiotemporal resolutions, instead have some different multi-resolution capabilities inside of our frames. And so those are portions of ongoing work that we're going after here. My lab is called Meteor Studio. You can look us up on the web. Send me a message if you're interested in this sort of activity, and I'd be happy to collaborate. Anyway, thank you for coming to the talk. I'm happy to take any questions.
Great. Thank you, Robert, for the exciting talk. We have a couple of questions. I'm releasing a poll for the audience. So if you want to see more talks like this, please answer that poll because it gives the tinyML community some feedback on the presentations. So I'll start off with this idea of fine-grained reconfigurability. One of the attendees asked, rather than switching resolution, would it be worth trying to have high resolution in the center of the vision and lowering the resolution far from the center? And maybe how would you start to investigate questions like this?
Yeah, that's an excellent question, because that's exactly what I'm trying to get after with both the contextual use cases as well as the fine-grained reconfigurability here. Foveated rendering is what you're talking about when you're trying to do that on the rendering side of things. And it turns out that people have been looking at foveated sensing as far back as the 90s that we've been seeing of different works that are looking at creating sensors that actually output at different resolutions depending on where you are inside of the sensor. For example, we saw a sensor that oriented its pixels in circular concentric fashion. And so instead of thinking of things in rectangular projections, thinking of them in polar projections. And so you'll have and they had a higher density of pixels at the center and a lower density on the rings. So people have been exploring that on the sensor levels, and people have been exploring this on the algorithm levels as well, because you can selectively use different pixels. But that's an excellent point, that we should be investigating this from the system support side of things as well, because it's not as, if you wait to do this in the visual computing side of things all the way at the algorithm level, then it's too late, because your sensed pixels have already entered your DRAM. And so what we have an active project on doing is to build a new kind of sensor interface that selectively, judiciously discards pixels along the way before they hit DRAM. And ideally before they even cross the camera sensor, the camera serial interface, before they even reach your system on chip. So if we are able to throw away those pixels, then we can have a multi-resolution frame where we have parts of the frame that are in high resolution, parts of the frames that are in lower resolutions. And part of our software-defined imaging effort with Suren and with Adrian Sampson from Cornell is how do we specify these as well, right? How do we insert these into the programming language, and how do we insert it into the programming ethos of visual computing application developers? How do we allow them to specify at at high granularities of where they want inside of the frame to be able to do things at high resolution and low resolution, and even high frame rate and low frame rate. And along with that kind of idea is that we want to be able to create policies that will relieve the application developers from having to even think about these in the first place. If the system is able to just automatically adapt to the visual scene and be able to then self-configure its multi-resolution behavior, then I think that would be where things really start to take off as well. So then developers get what they need, abstracted away, the system is implementing some really cool multi-resolution capabilities to get the visual information it needs, and the application developer still gets to develop the great application for their users. So that's kind of some of my thoughts on that topic.
Following up, Sean Doyle had a follow-up question. He was curious about this multi-resolution within the frames. Is this using wavelets? And I'm going to interpret this as like maybe like is the computation, is it suited for wavelets, or is it, how do you choose this multi-resolution within frames?
It definitely could be. It definitely could be related to wavelets. It could be related to wavelets because I think wavelets are one really great way to represent like JPEG 2000 style of information at different resolutions where needed, right? Where your image requires there to be high resolution, you can sample at that high resolution, and where the image requires you to be at low resolution, you can do so at low resolution, guided by the frequency of your wavelets. So that could be an excellent way to guide these kinds of policies that we're talking about and shaping. And so what we want to do is build a system support to take from those algorithms the specifications of what is needed, and then provide only the pixels that are needed and save the energy all along the way.
And the final question from Chandru Sarkala is, can you please share if there are any differences between RGB, IR, thermal image sensors? How will your methods accommodate for different modalities?
So these methods actually, the beauty of these methods is that we're dealing at a pixel abstraction level. And what that allows it to do is actually be useful for all of these different modalities that you expressed. Now, that being said, the different exposure time properties of them, the different specifications that are related to the timing characteristics of these sensors may change some of the properties here. And probably for IR frames, it is actually okay if you drop a frame. Well, it depends on your application, I guess. So, but in some cases, maybe seamless reconfiguration isn't a high priority, and just the concept of reconfiguration is important. For some sensors, reconfiguration isn't important at all because they are already low resolution, and so it's not necessary to go lower than that. And so those sorts of things are within our mindset as well. But generally speaking, if you've got a high resolution sensor of whatever wavelengths you're filtering your pixels at, we're still able to apply the same principles of being able to, for example, set the sensor into different standby modes to save power, to change the clock frequency to save power, to create these different media frameworks to process pixels through frame buffers without dropping any frames in between, and so on and so forth. So I think that a lot of these techniques are scalable to different wavelengths as well.
Okay, well, let's thank Robert again for a great talk. And I just want to remind the audience that this is not the end of the conversation. You can view these recorded video and slides on YouTube and the tinyML forums page, where you can ask additional questions, and Robert and his team will be able to answer that periodically. So don't feel like this is the end if you have some questions after this talk. So continuing on.
Yep, sorry.
And just a reminder, there's an active poll. Really take this quick 5-question poll. It helps give us feedback at the tinyML community about the talks and the programming and what you'd like to see. Again, I want to thank our tinyML talk sponsor, and I'll talk about each one of them briefly. DeepLight. DeepLight is interested in model compression, model optimization, and allowing you to deploy more models to your device without sacrificing performance or battery life. Edge Impulse is dedicated for tinyML for all developers. Maxim Integrated, enabling edge intelligence through signal conditioning, low power micros, and upcoming advanced AI acceleration. Kitso AutoML for embedded AI, that building tinyML solutions for the edge using sensor data. Reality AI, next generation AI tools for product development. SynSense for building ultra low power sensing and inference hardware for edge devices. Just a reminder, our next tinyML talks are next Tuesday, September 15th at 8 a.m. We have a great set of speakers. If you're interested in presenting both at this Phoenix local chapter or the global, please contact talks@tinyml.org. I also recommend to sign up for the meetup page. You can get all the information of the upcoming talks and sign up for the tinyML forums where you can connect with the broader community, ask your technical questions, and so on. And with that, I want to thank you for joining this seminar, and I hope everyone has a great day, evening, morning, night, afternoon. Thank you again.